All right. Welcome back, everybody. So I apologize a little bit for the out-of-order presentation of topics relative to your projects. I know that you got, at least some of you got some discussion of semaphores in sections on Thursday and Friday, and some of you got discussions of scheduling on Thursday and Friday. I'm not sure that everybody got everything. But anyway, I've been trying to work my way through these topics slowly so that we get them well. But if you remember, last time was a big setup. I know that's a whole week ago. But of synchronization problems that we run into when we're dealing with essentially shared state. And this particular example here of the deposit method, where we sort of get the account balance, we add something to it, we store it back, seems fine until you start talking about two threads interacting with each other, and you get an interleaving where essentially this particular interleaving makes it happen as if whatever deposit thread number 2 was doing never happened. Which you can imagine this would be bad for a bank. Actually, it'd probably be very good for a bank because they get your money and they don't have to keep track of the fact that they have your money. Nonetheless, basically, what this led to was our discussion of atomic operations, which are things that should not be divisible this way. And a great example of an atomic operation that we'd like for our algorithm here is that deposit method can't be split up. And so however we run it, either thread 1 gets to run all of its deposit and then thread 2 or vice versa, but we don't split things up. And much of parallel programming is about identifying your atomic operations and figuring out how to protect them. Now, when I say a lot of parallel programming, there's a lot of other programming frameworks that people have developed that are kind of higher level than what we're talking about right now that try to make it so you don't even have to worry about some of these things. But for now, let's worry about them. And so I wanted to make sure that this running example, did anybody have any questions on this running example here? This I think illustrates the problem very nicely. Yeah.
Cannot any operation be made atomic by disabling interrupts before enabling after giving interrupts is atomic itself?
So that's a good question. You mean any set of operations be made atomic by disabling interrupts and then re-enabling them afterwards? Is that the question? Yeah, so the answer to that is maybe. And a great example where disabling interrupts doesn't help you at all is when you have more than one processor, because disabling interrupts on one doesn't necessarily prevent the other one from doing anything. So a multiprocessor solution, in fact, oftentimes the interrupt disable doesn't help you. But if what you're dealing with is something inside the kernel on a single processor, then yes, you can make things atomic with interrupt enable and disable. Okay. Now, there are, I guess that's probably as good as I want to say that there now. It depends also, the one other thing I will say about that is if you actually have interleaving that's happening as a result of hyperthreading, then disabling interrupts might or might not help you because there's some interleaving still going on in the hardware. So you have to think through. Hyperthreading behaves very much like multiprocessing under some circumstances. Okay, good. So if you remember, last time we went through the too much milk solution and came up with, or too much milk problem, and came up with the following solution, which I guess is clever. It basically, if you remember, the problem was that you've got two roommates who are being very good about purchasing milk, and if they come in and they notice there's no milk, they're supposed to go out and buy some and bring it back, except if you actually work this through, you find out there are a number of race conditions where both of them go buy milk, and that was the too much milk. And so we went through a bunch of solutions and came up with this one, which basically was a way to make sure that you only bought one sort of half gallon of milk or whatever you're going after, and you didn't buy too many, and you definitely bought some, right? And The thing about this solution, if you look carefully, is it's all fine and dandy, but it's not even symmetrical. Thread A and thread B do different things. And the other big problem here is that thread A potentially has to spin looking at a note from B to decide whether B is going to go and buy milk or not. And then eventually, once B is no longer looking in the refrigerator, then A goes ahead and checks in the refrigerator. So there's busy waiting in here too, which is not desirable. But yeah, this works. Were there any questions on this solution? What are we assuming here? We're assuming there's some assumption that's going on in this, couple of them actually, but we'll only work on one for a moment. What's the key? Yeah. Okay, say it again. Leaving the node is atomic. That's correct. We're actually, right, and basically underlying the covers here are basically that loads and stores are atomic. Okay, that's kind of our main assumption here. And leaving the node, of course, is doing a store. Good. Okay, so that wasn't good. So we decided we wanted something better. And by the way, this is sort of, you go to a fraternity or sorority and suddenly this is complicated because every thread is different and they get successively more complicated. Okay, so you have 20 roommates, you definitely don't want to do this. And so that led us to this solution, which basically said, well, suppose we have a lock, whatever that is, then we might have an acquire and release. And by the way, now, since you are all experts in C, I'm kind of using more of a C syntax here, where the lock itself is being passed in, or an address of the lock is being passed into the acquire and the release. Okay? And if we had that, then we have to make sure that whatever they are, they're atomic. Then we could say our milk problem looks like this. We acquire a milk lock, we check if no milk by milk, and we release the milk lock. And that thing I've got in red in the middle there is the critical section. That's the thing that we want to make sure is done atomically by each of, whatever roommate happens to acquire the lock. They go in there and only one of them can check the milk and buy milk at a time. Okay? That's our solution to the milk problem. And this one scales really nicely. Of course, we don't know how to build locks yet, but that scales pretty nicely, assuming locks work. Okay? All right. And this is a critical section in the middle there. Oops. And, of course, you could make this much simpler by buying ice cream instead of milk, and then you can never have too much ice cream, but that's only my personal opinion. Were there any questions on this? What's buried? There's a lot of things buried in this solution, by the way. So what happens if two roommates both kind of approach the refrigerator at the same time? What's going to happen in this solution? Yeah.
Like the OS or something's going to have to make sure that only one of them actually acquires the lock, even if they run that at the same time.
Right. So suppose that both of them go try to acquire the lock at once, and only one of them is allowed to acquire the lock. What does that actually mean? What was that? Well, it does mean lock on lock, but what does it actually mean happens to the other roommate? Yeah. Something else, right? They got to wait. Okay, so the key thing about synchronization in this form is it's always about waiting. The way you make something work properly is you wait. Okay, if there's a chance where there'll be an interleaving that's bad, you force somebody to wait and the other one goes forward. And that waiting is buried inside that acquire. So whenever you look at an implementation of acquire, the question you ought to be asking is how is acquire implemented and what happens when you wait? And of course, the release method, whatever that is, obviously it has to relate to the acquire method. So whatever acquire does, release undoes it and maybe wakes up the next person for the lock. Okay? Are we good on that? I just wanted to make sure that we were all good. Any questions? Now notice, by the way I've written this, there can be a whole array of locks, okay? Because acquire and release are generic methods that take a lock in them as part of one of their arguments, okay? So whenever you look at a lock implementation, you're probably thinking that there can be many locks passed in as arguments. Or if we're doing a better language than C, sorry, that slipped out that way, we'd probably do something like we have locks that have acquire and release methods, and we'd say lock.acquire or lock.release, right? So if it were a quote-unquote real language, we would be better, but of course we're doing systems programming, so we're using C. Okay. Now, so the goals for today are basically to continue with this, talking about synchronization, and we're going to actually talk in more detail about better synchronization operations after we sort of do a little bit more with locking. And then I want to give a little bit of an introduction to scheduling. This is a little out of order. And then, assuming we have some extra time, I'm going to show you a more extended synchronization example, which I call the reader's-writer's problem. So this is where we're going. And let's start. If you remember, one of the things we did was we looked at a bunch of implementations of locks, and we said, well, here's an implementation of locking that uses disabling of interrupts that doesn't necessarily disable interrupts for the full critical section. Because the problem is that when you grab a lock and you do a bunch of stuff and then you release the lock, who knows how long the bunch of stuff takes? And if we're disabling interrupts the whole time, that could be very bad because, we could have a nuclear meltdown or something. And so that led to this kind of solution, which I, by the way, rewritten from last time in the glorious sort of C style. Okay, and so what you see here is there is a lock called mylock, which I'm going to set it to free, which could be in 0 or whatever, it doesn't matter here. And then I'm going to have acquire and release methods. You pass in an address to mylock. And then those, let's look at what acquire looks like. It actually takes in an address to an integer for the lock. We disable interrupts. We say if the lock is busy, do something, put the thread on a wait queue, go to sleep. Otherwise, we set the lock to busy and we exit and re-enable interrupts. So in theory at least, this implementation disables interrupts, checks some stuff, and re-enables them quickly. Okay, because the lock itself is that integer. And so all we're doing in this very quick disable and enable is manipulating mylock atomically, not the actual critical section that the user is trying to program. Okay, and here's the flip side of this. Of course, we disable interrupts. We sort of say, well, I'm about to release the lock, but does anybody else need it? And if so, I'll take somebody off the wait queue and let them run. Otherwise, I'm going to set the lock to free and re-enable interrupts. And notice, again, the idea is that hopefully what's inside here is very quick, and the disable and enable happens quickly. Okay? So why is this only good in the kernel? This is not a bad implementation, but why can we only use this inside the kernel? That's right. You do not want to let a user process control interrupts. Good. Why?
I have another question.
Okay, so why don't we want to let them disable interrupts?
Because if, say, it gets stuck in the middle of that code, then you're just going to hang forever.
That's right. If this is a user and they compute pi in the middle here to the last digit, we just crash the machine. Yes. Okay, now your second question.
So if you go to sleep in acquire, then interrupts will be enabled until
Yes. So that's a good question. When do we re-enable interrupts in here? And so clearly, this is not the whole story, which kind of led us to this slide, okay, from last time. And the idea here was that basically we enter the sleep or we enter the scheduler with interrupts disabled, and then when we go to schedule somebody else, we go to sleep, somebody else gets scheduled. By the way, that got out of position there a little bit. I'm not sure how. Better. Then what actually happens is it's the next thread that runs that re-enables interrupts. Okay? Because obviously if we left interrupts off and went to sleep and nobody else re-enabled them, we're in the same problem we were before. Okay? Good question. So why do we have to do this during a context switch or inside? Why are interrupts already off always in that section? This is perfectly natural, what I'm showing you here. Why is this perfectly natural to have interrupts off when we're context switching or switching or whatever?
Well, the values in the registers are copied individually, right? So, I mean, if you interrupt in the middle of that, then...
Yeah. Basically, switch is switching out a bunch of registers, switching in a bunch of registers. Any interrupt in the middle of that's likely to really screw things up. So that's why interrupts are typically off in the middle of the switch. And so that, hopefully that answered your question, right? So they get re-enabled by the next thread. Okay, good. Now, questions? Yeah.
So does that mean that whenever runs start, interrupts are always in a state of disabled? Like, it would make sense to me that like the OS would like track, like, restore the interrupt to whatever state it just was. So you're saying the OS always keeps interrupts off when it starts?
No, I'm saying that the interrupts are off when you're in the middle of the scheduler. Now, starting a thread, there's some stuff that the parent maybe does in starting the thread, and that doesn't need interrupts off. And then when you introduce the thread into the scheduler, that's the point at which you might need to have interrupts off while it gets put on a ready queue or a run queue. But it's just kind of that point when it's actually in the scheduling queue and getting pulled on and off where things definitely need to be off. And to take that a little further, think about that a second. Before the thread's actually running, it doesn't have any processor time. It doesn't, nobody's impacted by the fact that you're setting it up in some way. And so you don't have to worry about interrupts being off because it doesn't even have interrupts to turn on or off because it's data until it's actually instantiated inside on the ready queue and gets a thread control block. Okay, there was another question in the back? Or? Okay, good. So then we said, wait a minute, and I wanted to go through this a little bit quicker. Again, sorry for going over things. I just wanted to make sure everybody caught all these things. But notice that disabling of interrupts and enabling of interrupts, first of all, it can only be done in the kernel, and is kind of a heavyweight thing anyway. And so the question might be, is there a type of synchronization that we could do that we don't have to do in the kernel? Okay? And the answer is yes. And there's a whole bunch of types of read, modify, write operations or atomic operations that are in hardware that are typically introduced into processors. And I want to explain what this means. And for those of you that saw this last time, did anybody see these last time and kind of say, well, I don't understand what that was? A few of you? Okay. So what this means is each one of these things is actually a single instruction in the hardware. And as a single instruction, what it means is that all of the stuff inside of there is done atomically without interruption as an instruction. Now, the only exception is the very bottom one, which I'll explain separately in a moment. But what I want you to look at in particular is look at this test and set operation. This takes a memory address. Okay, this is a funny pseudocode, so I apologize. And what it does is atomically, without letting any other instructions in, it loads from that address and puts it in a register called result. It puts a 1 back into that memory, and then it returns the result. So as an instruction, it pulls a value out of memory, stores a 1 there, and returns the value that was there before, atomically. Tests and sets, atomically. And now we've already said this is already more sophisticated than a load or store, right? We now have new operations that we're using that are more sophisticated. Okay. Now, the other interesting ones here, compare and swap and swap. I mean, swap is kind of an obvious one where it says take a value in a register of the processor and a value and an address and store the register in the address and store the address back in the register and do that atomically so you can't be interrupted. That's swap. Okay? And then the last one here that's kind of interesting is compare and swap. And this is pretty powerful. What this one says is take the value in memory, check and see whether it matches the value you have in register 1, and if so, store register 2 back in memory. Compare first, then swap. Okay? That's a pretty powerful single instruction. All right. Now, the last one here is kind of a cool idea called load, linked, and store conditional, which takes a single address. And the idea is you load, think of this as assembly language, load linked the value in the memory into a register, do whatever you want for a critical section. You can do all sorts of stuff. And then when you go to store conditional, something back in that memory address, what happens is if somebody else has gotten in there and changed that out from under you, namely this is no longer atomic, you find out and you loop back and try it again, and you keep retrying until you discover it's atomic. And so this is a way of getting atomicity out of a sort of a loop of instructions. And I'm going to leave that one for you guys to think about because you don't have to worry about it now. Okay? More importantly for now, though, is the test and set probably and compare and swap are good ones. But let's even just talk about test and set, which we did last time, remember? And what we did with test and set was we said, here's how we implement a lock. So here is a different kind of lock that works perfectly well at user level. And by the way, I'm back to my simple pseudocode here for a moment. But you have an actual lock called myLock. You started at 0. What's acquire look like? It just is a while loop. It says while test and set the address of myLock. That's all it does. And release sets myLock to 0. Now, why does that work? Why is that an acquire and release of a lock? How would you even go about figuring out whether this is correct or not? What did we say earlier had to happen with acquire? Even though multiple people try acquire, what happens? Only one of them succeeds, right? So only one of them gets through the acquire. Everybody remember that? Well, if you look at this, what happens is we start this at 0. Everybody, let's say 12 million processors, that's a really big machine, come through and try to do test and set simultaneously. What's going to happen is every one of them is going to grab the value there and store a 1. Only the very first one that gets in there will actually grab a 0 and store a 1. Everybody else will grab a 1 and store a 1. Okay, so this is an atomic first come, first serve, you get there first, you win sort of instruction. And what does release do? Release just stores a 0 there again, says I'm done with the lock. Okay? Now notice what else is going on here. Everybody else who didn't get through the acquire is busy spinning because test and set returns a 1, which is a true condition for while, and they just keep going test and set, test and set, test and set, test and set, test. You get the, should I go for a little longer here? Test and set, right? So they keep testing and setting, and then somebody hits a 0, and the first one that tries the test and set again wins, and they get through because they get the 0 and they store a 1. All right, so this gives you an idea of the power of atomic instructions. Okay, and by the way, pretty much every processor that's worth its salt has at least a test and set these days. There were a few sort of notorious examples of mistakes, like MIPS was the first version of MIPS actually did not have an atomic test and set operation. They only had loads and stores, and by the way, they were stuck with buy milk number 3 solution. Okay, really didn't work well. All right. Now, the problem, of course, with this is you're busy waiting, right? Because those that are not acquiring, didn't successfully acquire, are busy spinning and wasting processor cycles doing nothing. And the other problem is this is actually really bad for caches. And let me explain. Everybody remember what a cache is? Okay, most of you use credit cards these days, right? So what a cache is, I don't know if I don't even carry cash with me anymore. So what a cache is, right, is a cache is a close-by piece of memory that I store something in so that if I access it again quickly, I get it much faster than going all the way to DRAM, right? That's a cache, spelled C-A-C-H-E. And the problem with this solution is that every test and set operation effectively is a write, not a read, because I'm always storing a 1. So basically this thing is anti-cache, because the only way caches work is if you read a lot, whereas everything's here is a write. So you put this on a multiprocessor or even on a multi-core, and you toast the whole machine, because you're just, all the traffic for cache coherence is a mess. Okay, and so that's an interesting problem, which we'll fix in a second with a very simple solution. Are there any questions on this? So now, let me say a little bit about busy waiting. So the positives of busy waiting are what? The machine can receive interrupts. Did we disable interrupts in here? No. Okay. User code. Can the user code use this lock? Yes. Test and set is a user mode instruction. Good. It works on a multiprocessor. Okay, for some definition it works, but what's interesting is multiprocessors that have cache coherent shared memory can just basically have a single lock in shared memory, and every processor can use test and set to synchronize, and it just works. Whereas the interrupt disable only works on one processor. Okay, so this is nice. Okay, negatives. This is extremely inefficient, because suppose you've got one processor and 5 threads. Okay, and what happens is one thread gets the lock and the next 4 get stuck spinning. What happens? Those 4 threads spin for a long time, each one at a time, because there's only one processor. The first one spins for 10 or 100 milliseconds, and then it hands it off to the second one, who spins for 100 milliseconds, and the third one spins for 100 milliseconds, and the fourth one spins for 100 milliseconds. And number 5, who was lucky enough to actually have the lock, now does a little computation for a while. And then we go back, and the first one spins for 100 milliseconds, right? So this is a big waste of cycles, because the very people that are waiting to get the lock freed are preventing the lock from being freed, because they're using up processor cycles. That's why busy waiting is almost always bad. Okay? So basically, the waiting thread's taking cycles away from the person holding the lock. Is that clear to everybody? Okay? Busy waiting, almost always bad. The other thing about busy waiting is priority inversion. So if the busy waiting thread has a higher priority than the thread holding the lock, then what happens? Well, now the busy waiting thread is going bzzz, and they're never going to get the lock, because the guy who's got the lock can't run because they're a lower priority. And by the way, this is exactly what happened to the original Mars rover. Had a type of priority inversion in the depths of the code that caused this problem. Yeah, go ahead.
Could you describe how red with higher priority is not able to hold on? It's not able to get to the fire lock code before, say, a lower priority thread?
Okay, so you're asking a more sophisticated question. How can a higher priority thread not get to the lock held by a lower priority thread? Okay, you ready for this? You need to have 3 threads to make this work. Okay, there's no 2-thread solution that has the problem you just said. Okay, you ready for this? Thread number 1 is the lowest priority, number 2 is the middle priority, number 3 is the highest priority. Thread number 1 has the lock. Thread number 3 tries to grab the lock but goes to sleep because thread number 1's got the lock. Number 2 is busy computing pi to the last digit. Okay? Game over. Well, you get a lot of digits of pi, which is always something close to my heart, but you may be not so thrilled with that, right? So that particular deadlock scenario does require 3 threads, but it is nonetheless a very, very bad scenario. Good question. All right. So we're going to talk about semaphores and monitors in a moment. But basically, semaphores and monitors are sufficiently high-level primitives that you could actually grab a lock and wait for a really long time, and that's kind of okay with the computation. But boy, if you got priority inversion, you got problems. So we don't want to busy wait. As a result, and I probably should have put this in red, if you give us a busy waiting solution for homework or exam solutions or in your project or whatever, we are going to ding you for it because busy waiting is just almost universally bad. except for the one example I'm going to give you in just a moment. And you're going to have to argue that that's your one example if you somehow give us busy waiting, okay? So let me tell you the one case where busy waiting works, and I suspect that you're not going to have this situation. The situation is you have a multiprocessor with n processors. N is what is arbitrary. And you've got some system with exactly n or less threads. Okay? Now that means that every thread gets its own processor. In that one instance, it's okay to busy wait, maybe. You have to argue that it's okay. Because the thread that has the lock gets to run by itself and it might eventually give it up, and then the thread waiting for the lock can grab it quickly. You're still wasting a lot of cycles, but maybe there was nothing else running there and that's exactly what you wanted to do. But I suspect that you're going to have to be a much more sophisticated multiprocessor parallel programmer before you get to busy waiting being a good thing. So we'll assume you're not and say that no busy waiting. Okay, questions? Now let me just show you, by the way, a typical use of test and set that is a much better version for multiprocessors, and it's called test and set. Okay? And by the way, don't worry, there's no test and set. Okay? So what test and set does is it looks like this. Basically, what you say is you continuously loop, and the first thing you say is while the lock is taken, spin. And as soon as it's not taken, then you go ahead and try test and set. And if you get a 1 back, you go back and try it again. Okay, and so this first one is, say, wait until it might be free. And the second one tries to atomically grab the lock. And only if you're the fortunate one that gets a 0 do you exit this loop. Otherwise, you go back and start all over again. We test first, and then we run test and set. And the reason this is, you basically wait till the lock might be free, and that wait until the lock might be free is a read-only scenario, so you're busy doing it in your cache. So your processor is spinning really fast in a single cache without bothering anybody else. Okay, and only when the write comes through to release, then you cause all of those caches to be invalidated. You notice some number of them notice that this is a 0. They go and try to do a test and set. One of them gets it and exits. The rest of them go back to spinning on their caches. Okay. The issue with this, of course, is it's still busy waiting. So you have to be in a scenario where busy waiting is still okay. Okay. Questions? Yeah.
Wait, when do you ever use this over just normal test and set?
Always. Yeah, you should never, ever use a vanilla test and set. Always use test and set. Because there really is no good reason to do a bunch of writes in a loop. It's just going to mess up your cache coherence bus. And I guess if you didn't have more than one processor, which is almost never today because everybody's got a multi-core. So, yeah. Sure. A cache being something that's keeping read things close to you so they're fast. So imagine that we're really talking about the mylock is in DRAM somewhere. When I do that while mylock, what's happening is I read it into my cache, and now I'm spinning looking at my cache over and over again until the situation where anybody writes it. Then I have to go back to DRAM and pull it back in. And so most of my spinning, which is that while mylock loop, is happening with my cache. Well, it's a non-interference thing. Don't interfere with any of the other processors. Okay, good. Now, can we build locks with test and set without busy waiting? Sure, we can do the same kind of thing we did before. And by the way, I'm going to assume you can put test and set in here if you want, because it's essentially the same thing. But we can do this, where essentially we say acquire takes a lock variable, and we sort of say this. We do while test and set on a guard variable. Then we do if lock busy, put it on the sleep queue and turn the guard to 0. Otherwise set lock to busy. And by the way, this guard is No, that's correct. That is correct. So, thought my formatting was wrong there. And this, by the way, if you look carefully at my disable interrupts, this is exactly the same thing where I've replaced the disable interrupt with the guard variable. It's exactly the same as that previous slide. Okay, and so now rather than forcing the user to disable and enable interrupts, what the user is doing is using test and set on a guard variable and then managing a whole, plethora of possible locks using what's in the middle there between test and between the test and set and the guard equals 0. And if you look carefully, you'll see this is almost identical to enabling and disabling interrupts, but now we can let the user do it and it works on a multiprocessor. Okay. Good. All right. Administrivia. First checkpoint is due Friday. And we decided 11:59 PST. So no AOE. I guess there were enough objections to that. Yes, this is a graded checkpoint. There was a couple of questions to that effect to TAs. I wanted to make sure that it was clear it is graded. And the other thing is, and we're going to remove some of the pseudocode in the design example document because it gives the wrong impression. This is supposed to be a high-level design document that you're producing as part of this checkpoint that think of it as a document you give to your manager who's your TA. Okay, you're not going to give your manager a bunch of code. Okay, so if you throw a whole bunch of code into your design document, that's just a bad idea. Okay, you're trying to give high-level, what are the ideas? Maybe a little pseudocode if it helps. Do not throw a bunch of code in there. Okay, this is not an example where the more pages wins. Okay, that's not the right way to look at this. Okay, now on the first checkpoint, you can breathe deeply, relax for a second. What's going to happen is we're going to give you comments on your style and sort of help you know where you went awry on that. We're going to ramp up on style checking later. Okay? So one of the things, let's see. The other thing is there's going to be sign-ups. Since this checkpoint's due on Friday, you need to sign up for the actual design review. And so watch for postings on Piazza. That's going to happen shortly thereafter. So make sure you look. Your TA is going to post design review slots, and you need to hook up with them as a group. And everybody in the group needs to be at the design review. Okay, people who don't show to design reviews get dinged. You lose points for that. Okay? We probably won't take points from your partners, but we'll certainly take points from you if you're not there. All right. The other thing is, and we haven't actually written any code yet, but actually writing a little bit of code. I would say do your own work. Okay, don't be looking for solutions. Okay, don't be posting for solutions because we are watching out for things like this. So just do your own work and everything will be great. Okay. Basic semaphores should work in Pintos, okay? I realize I gave sort of a wrong impression to somebody who came to my office hours. They do work, they just don't work with priority scheduling or any of that. So you're going to need to alter the ready queue structure and the semaphores to handle priority scheduling. That's part of what you're doing for this lab, okay? And then these sections, Thursday and Friday, are looking better, but it'd be good to get more people in them. And by the way, it would be good if you can attend the section for your TA that's in charge of your project, if at all possible. That would be a good way to get participation points and have them know you. And actually, if everybody attended the section they're assigned, whose TA is assigned to them, we'd have completely even sections. But I realize that's not entirely going to happen. But do your best. Are there any questions? Yeah.
What if our TA has a design review after the due date?
Well, the design reviews are after the due date. No, what you're doing is you're presenting your design document, and then you're going to talk through your design with them at the design review. And there'll be a chance to revise this document over time. So part of the reason of the design review is to really make it clear what your intended design is. And so actually, if you have a TA who's got a design review before the checkpoint is due, then that's a bug. That shouldn't happen. Okay, good. Other question? Yeah.
Roger has a bunch of reviews on Friday before 11 p.m.
Well, I guess what he's assuming is you'll turn it in, then do his review or something. But you should have your checkpoints turned in before your design review if you can. That's probably a constraint. I don't know. You could talk with him about it. Okay. All right, good. So I wanted to throw a fun example out of here. Here's compare and swap. Let me just show you. Here's an atomic add to linked list function. So normally, you might imagine that if you're trying to manage a list, and a lot of people are all dealing with the list at the same time, you need a lock in order to make that work. So the answer is you don't actually. What you can do is the following. You can say, here's the thing I want to add to my linked list. I can load the root of my list into a register, and I can store that link into the object, and I can say until a compare and swap succeeds. And if you look here, here's the original linked list. This is a singly linked list, by the way. If what I do here is I load this root pointer, I store it in my object. Notice how I'm setting up to link it in. And then I want to set the root equal to point to this guy, and then suddenly he'll be in the list, right? And what I do here is I say I want to do a compare and swap to see is the root variable still pointing at the original guy here, and if so, object gets stored in the root. So this basically says as long as this link has been left alone, go ahead and change it to that link. And this will work no matter how many simultaneous things are trying to link in the list. And notice this very slight loop here, this do until, basically catches those cases where there's a race condition. Right? So this is what we call lock-free, because there's no lock in here, style computation. And so there's several interesting ways you can use lock-free methods, but we're not going to go into it anymore right now. All right? Question? What was this? Well, actually, it turns out that Intel's actually got a compare and swap operation too. So, okay. All right. So now let's move on. So let's talk about some higher level primitives than locks. So the goal of the last couple lectures has really been asking ourselves what's the right abstraction for synchronizing threads, and we'd like to have as high a level primitive as possible to make it easy to work with. And good primitives are going to be very important. You've already heard my sort of rant about, because we have non-deterministic execution and Heisenbugs, we better make sure that things are designed right from the beginning, because we're certainly not going to catch bugs via testing. Okay? And Unix is a very good example of a bad initial implementation where it was unstable. How many people, by the way, have a laptop where the default solution when something bad is to reboot? Okay. I won't say what company it's probably made by, but that happens. Okay. So synchronizing is basically a way of coordinating multiple coherent activities. And this lecture and the next, to some extent, is going to give you a couple of ways to think about that are more than just locks. So locks, you're starting to get the flavor for locks. You identify your critical section, you grab a lock before you do something, you release the lock. It turns out that works, but by the time you start asking for the correctness of a really complicated application, now suddenly the question is, do I have the right locks in the right places? Did I grab them in the right orders? And it gets very complicated very quickly. So one thing which now you're increasingly familiar with is a semaphore. And a semaphore was first defined by Dijkstra in the late 60s, and it's basically the main synchronization primitive in the original Unix and a lot of operating systems, including PinTOS. Okay? And what is a semaphore? It's a type of integer almost. It has a non-negative integer value and supports two operations and two operations only. One is P, which is an atomic operation that waits for the semaphore to become positive and then decrements it by 1. And V, which increments the semaphore by 1 and wakes up some waiting P if there are any. So you could think of this first thing like wait and the second thing like signal. Okay? And by the way, sometimes people that don't like P and V call this what? Well, we're decrementing down and up or whatever. There's lots of different ways. P and V, you know you're cool when you use P and V. So P is probieren for test, and V is verhogen for increment in Deutsch. Okay? So P and V, all right, are the real semaphores. Now, where did that come from? From Dijkstra, okay? Because he's the one that developed this. And so semaphores are like integers except what? So no negative values. So they're more like whole numbers maybe. Only operations are P and V, so you can't actually read or write the value, except when you create it. The only time you ever set the value of a semaphore is on creation. Okay? And operations are atomic. So two P's together can never decrement below 0 because P and V are fully atomic. So if you look carefully here, by the way, what does P do? So P says, waits for the semaphore to become positive and then decrement by 1. What that basically says there is there's absolutely no way by executing a lot of P's together to ever get below 0. That's not allowed in a semaphore. Okay? And similarly, and notice, by the way, that the default, if you would go below 0, is you wait. So this is going to be our synchronizing operation. Just like in a lock, when you tried to acquire and somebody else had it, what did you do? Wait, right? Notice also with V, basically when we increment the semaphore above 0, it better not be the case that somebody's waiting, because then we've violated our constraints there too. So semaphore bigger than 0, there's nobody waiting on it. A semaphore can never go below 0. All right. So, and basically, thread going to sleep in a P won't miss a wake up from V. So if you have a P and a V happening simultaneously, there's no way to interleave them that will violate those constraints either. Okay? That's the implementer of the semaphore does that for you, and then you can think that that's the right behavior when you're using it. Okay, and by the way, when you're messing around with your semaphores, you're adding various functionality to it. Be sure that you don't violate these constraints. Okay, it should not be the case that you have somebody sleeping when the value is greater than 1 or greater than 0, or you got a problem. So semaphore comes from a railway analogy. All right, so you ready? This is PowerPoint fun. So here's a semaphore initialized to 2. So first and foremost, we already know this is somehow different from a lock because we got the number 2 in here. Okay? And watch what happens. So this is a track. There's the semaphore. It's got a value of 2. Here comes a train. If you notice, sorry, I clicked too fast. The first one came through, did a P operation, and basically decremented from 2 to 1. No problem. We went through the semaphore. The second one comes along, goes through the semaphore, no problem, executing a P. But now what's the semaphore equal to? 0. So what's going to happen when the next train comes along and tries to execute a P operation? Yeah. Wait. Okay. And now when one of the trains decides to exit the critical section, and I'm going to put that in quotes, it's going to execute a V to increment. And what happens? We execute a V that immediately causes this to go from 0 to 1, which causes the train that was waiting to go through, which decrements it to 0 again. Okay, should we try this again? Ready? Okay, there's the train. Here comes train number 1. A P goes to 1. Next train takes it to 0. Third train can't move. It's stuck. When a train executes V, it increments to 0, from 0 to 1, but only long enough until we release the guy waiting and we go through. Okay, that's a semaphore in all its glory. And notice that I can initialize value to anything I want. It's non-negative. I can initialize value to 0. What happens if I start a semaphore at... Oh, go ahead, ask a question.
I
I'll show you in a sec. So notice, by the way, what this said here, by setting the value to 2, I've said effectively that there can only be 2 trains in the yard. If I set it to 1, there could only be 1 train in the yard. Okay? In this analogy, if I set it to 0, I'm in trouble because no trains can get through the yard. Okay? Is there ever an instance anybody can think of where it would make sense to set an initial value to 0? Yeah.
Let's say you want to have something be waiting for something else, and then you just up it later in time.
Perfect. Everybody catch that? If I want to have something waiting for something else, I initialize to 0 and I immediately do a P. I'm waiting. And now somebody does a V on that same semaphore and they wake me up and I go forward. That's a wait for condition. Okay, so you can start to see why 0, 1, and greater than 1, whatever it might be, are all sorts of use cases for semaphores. Okay, they're much more powerful than a lock. Now, here's a good example of 2 definite, very different uses. So one is mutual exclusion, which is often the word mutex, you've probably seen that, or a binary semaphore. And what I do there is I set it to 1. And now this is very much like a lock, because I enter the critical section by doing a P operation and I exit by doing a V. If 2 folks try to do P at the same time, it's exactly like trying to do 2 acquires. One of them will wait, the other one gets to go through. And as soon as I do the V operation, the guy that's waiting wakes up and goes through again and acquires the lock. Okay? Here's another completely different usage. Here's a scheduling constraint. I set the value to 0. We just said this a moment ago. And basically, locks are fine for mutual exclusion, but what if you want to do somebody to wait for something? We already said this. You basically, here's a thread join and a thread finish. What this says is the parent executes a P operation, then the child on its way out executes V, thereby waking up the parent. Okay? So those are 2 extremely different uses of semaphores. And you can't do this with a lock, really. I mean, you could acquire the lock and then pass it to the child and then have the child, tricky, not as clean. Okay. So let me just show you a producer-consumer with a bounded buffer example. So here, the problem here is one that everybody can appreciate. We need a Coke machine anywhere there's lab space, right? Obviously, because you need Coke in the middle of the night, and I'm talking about Coca-Cola. And so here, don't get too excited. So here, the producer is the one that's bringing the cans of soda and putting it in the shared buffer, and the consumer is going to take them out. That's you guys. And we need a way to synchronize and coordinate the producer and consumer because this buffer is the machine. All right? And we don't want the producer and the consumer to have to work in lockstep. We want them to just work asynchronously. So we put in a fixed size buffer, and this fixed size buffer, like the Coca-Cola machine. And obviously what needs to happen here is, for instance, the buffer itself probably involves a linked list or something like that, which means that we got to put locks around it, otherwise it's going to get messed up. Okay, I'm going to put something on a linked list, I grab the lock for the list, I put it on the list, I release the lock. So we need to synchronize access to the buffer, and also the producer needs to go and wait if the buffer is full. So if there's all the soda is filled up in here, the producer can't put more soda in, it's got to wait. Similarly, if you're desperately waiting for a Coca-Cola, you go to try to grab it off of an empty machine, what do? Well, you take a nap in front of the machine until the guy comes with Coke, right? Okay. So, now, by the way, a good example that's not a Coke machine here is what you just saw here with pipes. So here's an example where the GCC compiler, we have the C preprocessor, produces stuff that gets used by the first and second passes of the compiler, and then the assembler and the loader. And C preprocessor is pushing stuff out that's getting input to CC1 and so on. That's a great example of a bounded buffer because it's a FIFO queue of finite size. It's a FIFO queue of finite size. The second thing here is the Coke machine I just gave you example, and I want to pull this out for a moment. So our correctness constraints for this solution are: the consumer must wait for the producer to fill buffers if there aren't any buffers that are full. The producer must wait for the consumer if the buffers are completely full, and only one thread can manipulate the buffer at a time. Okay, those are our correctness constraints. How many constraints are they? 1, 2, 3. How many semaphores are we going to use? 3. Okay. And by the way, why do we need mutual exclusion? Because computers are really stupid. This is what led us to our got milk solution. And so here, as a rule of thumb, you use a separate semaphore for each constraint. And so our 3 semaphores are the full buffer semaphore, the empty buffer semaphore, and the mutex. The full buffer semaphore is the consumer's constraint, the empty buffer semaphore is the producer's constraint, and the mutex is to help us make sure that the buffer manipulation works well. And so here's a full solution. I'll just put this out here. We start the full buffer constraint at 0 because initially there's no Coke in the machine. And therefore, if a student comes along and tries to take a Coke out of that machine, they're going to execute a P operation on the full buffer, and they're going to go to sleep in front of it. Similarly, notice how empty buffers is the whole machine initially, because it's an empty machine, and therefore all of the buffers are empty. Okay? There are num buffers, empty buffers. And then the mutex, which we're going to use like a lock, we start equal to 1. And so now look at our producer and consumer. The producer says, oh, I do an empty buffer.p, which says basically wait until there's space. Then I grab the mutex lock, mutex.p. I enqueue the item on the queue. So this is something which is probably a multiple operation thing which needs to be atomic. Remember the last time you did a doubly linked list, right? You got to set up the multiple pointers. And so if I'm going to enqueue something on my list, I better make sure to grab the lock, mutex.p, release the lock, mutex.b. Okay? And then the last thing I do is I say full buffers.v, which says I just produced a Coke in the machine. One student who happens to be sleeping gets to get woken up. Okay, and then the flip side is exactly the flip side. The first thing I do is I say, well, I want to get a Coke, so I try to execute full buffer.p. If there's no Coke in the machine, this will be 0 and I'll go to sleep. But assuming I get past this, then I go ahead and get the lock, dequeue the item, release the lock, and then indicate to the Coke machine guy that there's one free buffer slot if he needs it, and then I return the item to me. There you go. Okay, there's 3 different types of semaphores, well, 2 sort of resource constraints and 1 mutex semaphore in its full glory. Any questions? Yeah.
What would happen if you reordered empty buffers and mutex?
That's a darn good question. So let's talk about this. So why is it asymmetric in the following way? So the producer does empty buffer, full buffer V. The consumer does full buffer P, empty buffer V. So before we answer the reordering question, why is it that the producer does empty buffer.p and full buffer.v? We're getting to your question in just a second. So why do we do this? Empty buffer.p says... Well, so basically this says, if they can't put any more Coke in the machine, I better go to sleep. Right? So this is waiting to see if there is one buffer slot. That's why we do a .p. And this says, oh, gee, I put some Coke in there. Wake up one person who's waiting. The flip side is the consumer sleeps until they've got something. That's full buffer.p. And then they indicate that there's a new empty buffer to the producer. Okay, that's why these are done this way. Now, the interesting thing is this order of P's, okay? And the answer to your question is yes, it matters. Okay, and if you look carefully here, what would happen if we did it this way? Mutex.p followed by empty buffers.p. Okay, does everybody see why that could deadlock? Okay, the problem is, gee, we got lucky and grabbed the mutex, and then we tried empty buffers.p, but that basically put us to sleep because there's no space in the machine. And now, sometime later, you, a student, come by and you want to grab a Coke, and somewhere along the line, you need to execute a mutex.p to grab the lock, and you can't because the producer's got it and he's sleeping. So we've just deadlocked. Okay? So this is an interesting situation where you got to be careful. And actually, this is kind of a good example of why semaphores have downsides. Yeah, go ahead.
Does the order of releasing the semaphores matter?
So surprising you should ask that. So is the order of the V's important? No. However, so the reason it's not important is because I can say, wake up, wake up, wake up, wake up in whatever order, and there's no way that that's going to block me, and so I'm waking people up as I go. All right? But it may be that there's some scheduling efficiency in this where the first one I wake up gets to run, and then they actually release the lock, so the second guy I wake up goes forward. But and so the order that we gave you, kind of this inside out, is a nice order, but yeah, that one is not going to change the deadlock ability of this. Yeah. Because, okay, so that's a good question. So you're wondering why we have the mutex around the NQ and DQ?
Right, because one thing can only write and one thing can only read. So that should be...
So it is and it isn't. So it turns out if you take just a regular doubly linked list like you learn about in 61B where you manipulate multiple pointers and so on, if you have two people working on that list at the same time, it's going to get screwed up if there's parallelism in there. And you really need to put a lock around it, otherwise you're going to get screwed up. There are lock-free versions, kind of like what I showed you earlier, of NQ and DQ that can work without locks around them, but they're much harder to get right, and they don't always work unless you know exactly what you're doing.
Right, but even if you're using a doubly linked list, the consumer isn't really changing any pointers.
Sure they are, because they're pulling something off the list. So they have to change the head and the tail pointer. Right? So they're manipulating shared state. Yeah, go ahead.
Kind of related to that, is there any situation where there's a full buffer is available, but the machine is not free? Like given this ordering of all the
Full buffers, so there is so you're saying there is a buffer that's available for the consumer, so you do full buffers.p. And so what's the scenario you're worried about here?
Well, it seems like the mutexes aren't necessary for the consumer. Because if there's a full buffer, I don't think there's any situation.
Well, notice that this, by the way, all this is saying is that there's any buffer, not that the buffers are completely full. So even if there's one Coke in the machine, I'm going to pass through this full buffers.p because there's one full buffer. But then the producer may be busy putting other Coke in there. So you have to still have the mutex in the middle there. Good question, though. See that?
So if it's just like there's only one spot.
Well, if we have a single buffer with a single queue item, then yeah, you don't need this complexity. But that's a much less interesting bounded buffer. Okay. So good. So what if we have two producers and two consumers? Can we deal with multiple Coke machine guys and multiple students? How many people think that this works fine with many producers and many students? Okay? How many people think it doesn't? How many people are not sure? So this actually works with multiple producers and consumers. Okay. All right, so before we take a brief break, I want to say the semaphores are a huge step up, but they're confusing because they have dual purpose. Both mutual exclusion and scheduling constraints are handled together in that ordering thing that you saw earlier. Gee, I got my P variables misordered, and as a result, I got deadlocked. That's a problem. And so a much cleaner idea is to use locks for mutual exclusion and condition variables for scheduling constraints. And when you put those together, you get what's called a monitor. And the definition is a monitor is a lock and 0 or more condition variables. Obviously, the 0 part is not very interesting. It's just a lock, right? But a lock is a lock plus 0 or more condition variables gives me a monitor. And the monitor is a programming pattern that is embodied directly in several languages. So, for instance, Java gives you monitors natively in the language. And I'll show you that next time. All right? And basically, the lock provides mutual exclusion to shared data. And it's always the case. You always acquire before accessing shared data, and you always release after finishing with shared data, and you start the lock as free. Okay, these are rules that you just follow. Okay? All right. And so if you look, actually, this is from the dinosaur book. They show this picture here. So a monitor is a complete pattern of code and data. The lock basically provides mutual exclusion to the shared data, and the condition variables are queues of threads that waiting for something inside a critical section. So now this is a crucial difference between what we normally think of with locks. Normally, if you grab a lock and then you go to sleep inside the lock critical section, we say that's a bad idea. Unless you're in the kernel and you're dealing with the scheduler directly, which I showed you a slide earlier. Okay, normally as a user, you should never grab a lock and go to sleep unless you're using a monitor. Then it's okay. Okay, because they've been designed to work that way. Okay, and I want to show you a really simple example of a monitor. So here's an infinitely synchronized queue. And basically it says the following. We add to queue by saying lock.acquire, in queue the item, lock.release. Okay? And the way we remove from the queue is we grab the lock, we dequeue, we release the lock, and we return the item. And that item could be null if there was nothing to dequeue. Okay, now most of you are like, wait a minute, that's boring, there's only a lock, there's no condition variables. How many people see there's no condition variables here? Okay, there aren't. Technically, this is a monitor. Okay, we'll call this the degenerate, not very interesting use case of a monitor, but technically this is a monitor. It uses a lock with no condition variables. Okay, now, I'm sorry, I missed your break. People want a break, or should we just finish up? We've got about 10 minutes. I apologize. Should we finish up? I wanted to say a little bit about scheduling today, too, so hopefully we can do that. Sorry about that. Condition variables. So let's change this remove from queue to be more interesting. So what would we really want remove from queue to do? Thinking back to the Coke example, what would we like remove from queue to actually do here? Rather than returning null, what would be better? Say again? Okay. What's going to happen to the guy that tries to dequeue when there's nothing on the queue? What should happen? Wait. Wouldn't it be nice if we waited? Right? Okay, so if you look here, let's try to do this by keeping a count of the number of things, and then we're going to use a condition variable, a single one, which again is a queue of threads waiting for something inside a critical section, and we're going to use that single one in the following way. So condition variables have three operations: wait, signal, and broadcast. Wait typically has to have a pointer to a lock, unless you have a more sophisticated language. Signal will wake up one waiter if there are any, and broadcast will wake up all the waiters. And let's look at this. Okay, the rule, by the way, don't forget, the rule is you always have to hold the lock when doing any condition variable operations. Okay, you can ignore papers that tell you otherwise. This is a pattern you should stick with. And here's how we do it. Okay, here's the code. Notice I've declared a lock, I've declared a condition variable called data ready, and I've declared a queue, which is just your good old-fashioned doubly linked list queue thing. And notice that what happens here is that add to queue acquires the lock and queues the item and then says signal and then releases. Okay, so notice that what's different here now is I'm saying that if anybody's sleeping, waiting for an incoming queue item, wake them up. That's what signal means. And now if you look at the flip side, when I go to remove, what I say is the following. I do lock.acquire, grab the lock, and then I say, while the queue is empty, wait. And this loop in principle might happen multiple times, but eventually I find that the queue is not empty. I exit by dequeuing, I do lock.release, and I return an item. And what's different in this case is that I always return a non-null item. And despite that while loop, the semantics are data.ready.wait actually puts me to sleep and doesn't use any cycles until somebody signals me. Question, yes? Why use a while loop? That's a really good question. So let's suppose we answer that question in the following way. So you need to be very careful about the precise definition of signal and wait. So consider a piece of our DQ code. What you see here is the while queue.empty data.ready.wait, and you're asking about that. And it turns out that you might ask, why didn't we do this? That seems like your question, right? You could say, well, Professor Kuby, why didn't we say if queue.isEmpty? Why didn't we do that? Yes?
You do that, you don't know that the queue really has an item on it.
Yeah. So we don't know that the queue really has an item on it. Well, in fact, this is really actually depends on the type of scheduler you have. Okay, there are two types of scheduling. There's something called Hoare-style scheduling, which is named after the person who originally came up with this, in which the signaler gives the lock immediately to one person he just woke up, and that person immediately wakes up and runs, and you know for a fact that there will be something on that queue. Okay, so in that instance, that second version of this with the if would work perfectly fine, because I'd say if queue is empty, okay, wait, and when I wake up, golly gee, how's that for funny? Well, I would know for a fact that the queue.dq is going to work and have a non-empty thing. The problem is that this is kind of messy to implement. There's been times in the past where I've made you implement this on exams with semaphores, but who knows? Mesa style, which is pretty much what all operating systems actually use, is a little different. The signaler just keeps going with the lock, and they take the guy they signaled and put him on the ready queue. Does that sound familiar, by the way, for what you're supposed to be doing? And you're doing it with semaphores. So the signaler keeps the lock, puts the guy on the ready queue, and keeps running. And the downside of that style is that when the guy who got woken up finally gets to run, it may be that somebody else has grabbed the item out from under them. And therefore, we have to keep checking and going to sleep and waking up. But I want you to notice something really weird about this, and I'm going to say this because we're running low on time. Notice that I'm inside of a critical section. I did lock acquire, and therefore that while is inside the critical section. So you might ask the question, how is it possible that somebody else could come in and steal this away from me? And that's the magic of monitors, because what happens under the covers is, I go to sleep, I release the lock, I give it to somebody else. And it's only when I come back to run again that I have the lock for sure. So the only thing I know for sure is that I can, as a programmer, think of this section of code as always having the lock. That's a completely okay way to think about it, even though it's not strictly true. And so when I say while queue is empty, if this comes out false and I fall through this, I have the lock, so it's not possible at the point that while loop is false for anybody to come in and steal it from me, so I go ahead and grab it. So the way you think about monitors is you think about them as if you grab the lock, you check some conditions. When they're not good, you go to sleep, you keep checking them. When the conditions are true, you go ahead and do something as if the conditions are absolutely true and nobody came in there and messed up with you because you're in the middle of a critical section. Okay? Question? Now, by the way, next time I'm going to give you a more extended example of this so you can get a better handle on it. But I wanted to give you this initial thought, okay? Now, so I wanted to very quickly talk about scheduling in our last 5 minutes. So if you remember, I gave you a diagram like this, maybe even the first day or second day, whatever. And I said, look, here's what's happening with CPU scheduling. And what I said is there's this ready queue thing where we keep pulling things off the ready queue, giving them to the CPU, and then eventually the time slice maybe expires and we put them back on the ready queue. And there is this loop of threads that are ready to run. And this is, by the way, something that you're starting to become familiar with because you're messing with the ready queue. You're starting to think about messing with the ready queue. That is only one queue of many in the system. And remember, I kind of said, gee, there's sort of other wait queues. Okay? And the interesting questions you should ask is, first of all, what are the wait queues in the system? Well, a good example of the wait queue is something like the lock acquire has a wait queue, or semaphore has a wait queue. So those are examples of threads that are removed from the ready queue and put on these other queues, and then when you wake somebody up, you take it off of that wait queue and put it back on the ready queue. Okay, so things are not even on the ready queue when they're asleep in a lock. Okay? The other interesting question about this is when you have any queue, either a wait queue or the ready queue, the question might be, how do I decide of these 20 things on the queue, which one goes next? Okay, suppose there are 20 items on the ready queue. How do I decide which one to run on the CPU next? What are some good examples of things I might want? Well, grab the highest priority thing. Grab the next thing. Grab the thing that's likely to have the shortest runtime. Okay, these are all scheduling, right? And so scheduling assumptions, there are many, it was a big area of research. We're going to spend some time definitely with this next week. Many implicit assumptions that we'll go into. And clearly, a lot of these assumptions were unrealistic, but you can start asking questions about, suppose I want things to be fair in my scheduling. What does that mean? Well, everybody gets the same amount of CPU time, whatever. Okay, and again, these are not things you have to worry about right now until next week, but the high-level goal is basically dole out CPU time according to some scheduling policy. Okay, and it's really about how do I take things off of the ready queue and put them on to the CPU and vice versa, or how do I take them off of the wait queue? I've got a semaphore. I've got priority threads. I do a V operation and wake somebody up. What thread do I pull off of there? I probably pull one of the high priority threads off because they're the ones that ought to run. These are all scheduling decisions, okay? And there are many goals. You might want to minimize the response time to a user. You might want to maximize throughput. You might want to worry about fairness. These are all very interesting things. But it's all about pull something off of the ready queue and give it to the CPU, and it's deciding which thing to pull off of the ready queue. Which thing? There are 20 of them. Which thread? Okay, and there's many things, and I wanted to leave you with at least 2 of them. First come, first serve, or FIFO scheduling, basically says, take the first thing off the ready queue and run it till it's done. Grab the next thing, run it till it's done. Okay? So a great example here are 3 processes, P1, P2, P3, burst times of 24, 3, and 3. And here is a possible order for running them on a CPU. You run P1 until it's done, then you run P2, then you run P3. Who does this? The scheduler pulls the first one off, gives it to the CPU. Pulls the second one off, gives it to the CPU. Okay? I'm just giving you this and for a thought here. And notice the waiting time. P1 doesn't wait at all. P2 waits 24 before it runs, and P3 waits 27 before they run. Okay? So we can start talking about waiting time. And we can come up with an average waiting time, 17, for instance. Now, obviously, an average completion time. We wouldn't get out of this without talking about the milk line, because milk seems to be the topic for the last couple of lectures, at the supermarket. So there's a convoy effect here, right? short process stuck behind the long ones. What is this? This is you're in the milk line. You got a one item, and you want to go to the quick line, and somebody brought a cart full of sausages, right? And they're in front of you. Okay, what do? Okay, and what's interesting about first come, first served scheduling is here's a different schedule of the same processes where I take P2 and P3 first and then P1. Notice that the average times are all shorter. So in fact, everybody's kind of happy here. Okay, and in the second case here, average wait time is much better. Before it was 17. Average completion time much better. Before it was 27. And the pros and cons here is it's simple for FIFO, but the short jobs get stuck behind the long ones, and this is the Safeway analogy of trying to get milk. Okay, and what you do in those scenarios is you read about space aliens or the latest thing with the royal family or something. I mean, there's always good stuff there. Kardashians, right? Okay. So anyway, I'm going to leave you with that. Next time we'll talk about round robin and a couple other things. Hold on. I wanted to say one thing here because you're going to hear about this question of a multi-level scheduler. And basically that's going to be a scheduler with multiple queues, each of which potentially have different quanta and different priorities. And things kind of flow their way through the different scheduling queues. Okay? We'll leave that for your TAs to talk about a little bit more. So in conclusion, we talked about semaphores. They're like integers with a restricted interface, only two operations, P and V. They're atomic. We talked about monitors, which are a lock and one or more condition variables. And we started talking about scheduling, and next time we'll talk about a bunch of scheduling. So I hope you guys have a great weekend. We'll see you on Monday. Good luck.